to figure out what to. Okay, so here we are in our little mechatronics journey. We're down here. We started out with basics, and we're going to do some little control of servos, and that's going to be. Here's a picture of a servo up here. Servos are going to be critical to your final project. We're going to be using a lot of servos. Okay, so here's our feedback control loop we've been using as our model. Here we're going to talk about actors for a second, for just one lesson. We're going to talk about servos and how to make servos turn. Logically, this might come way later in the course, and you may have noticed the reading for today was from chapter 23. We went way to the back of the book. That's because I think it'll be a little bit more fun if we can get some things moving right away in the course, actually make things turn, make things do something, because as mechanical engineers, we tend to enjoy that, and it'll help you see why we're learning the things we're learning. So here we're going to focus on, in this lesson, we're focusing on how do we use the microcontroller to make an actuator do something. We're not really getting into feedback yet. That'll come a little bit later. Although that little board work exercise we just did was using sensors and feedback. Okay, so what is a servo? Here's some pictures. I've got one here on my desk. I'll show you if you can see my little avatar down in the bottom corner. There's a hobby servo, Futaba. Here's a couple examples of a cutaway of a servo. So a servo is like a DC motor, but it has some extra stuff. And here I'm holding up a simple DC motor. This is a very inexpensive, unsophisticated one. It just has a coil of wires and 2 leads. You put power on one lead and ground on the other, and it will spin in one direction. And if you flip the power and ground, it'll spin in the other direction. Well, servo is more sophisticated in that it has a control circuit in it. So it has the DC motor, just like the one I just showed you, but it also has a gearbox to slow it down. If we plugged in this DC motor by itself, can you guys see me when I'm showing you stuff? Because I know I'm displaying the slides.
Yes, sir, in the corner there.
Yeah, you see me in the corner. Okay, so I've got a 9-volt battery in this little DC motor. Oh, there we go. Maybe the battery's dead. Did you see it spinning there? And it spins pretty fast. For those who have played with servos, is this faster or slower than a servo?
That's faster than
faster.
Way faster. Okay. So my point is, a servo's got these gears on it to slow it down. Because generally we want to use a servo for positioning. Something you might be familiar with, like hobby race cars or airplanes, they use servos to say, so on an airplane, you use a servo to control the flight control surfaces on your airplane, rudder, ailerons, elevator, things like that. You're not spinning something really fast. You wouldn't use a servo to spin the propeller on your airplane, but you would use it to do small positioning of your elevator, your ailerons. Okay, so we've got gears to slow it down. Then it's got a control circuit, which has a sensor, probably a magnetic sensor, but it could be a physical potentiometer, which is what's shown in this picture. And it's going to try to hold the servo at a certain position. And so the commands we send it are directed at a certain position. Okay, so why do we use servos? How do we control servos? So here's a really interesting example. There's a servo. So this is a close-up view of an RC car's speed control. Okay, so this is mechanical control of a DC motor. Now what's interesting in here is there's probably a servo attached to this. You see this silver rod? That is probably attached to a servo, which is going to turn this rotor and slide this paddle across this thing. What's this shiny thing? Anyone know?
Those look like coils, maybe? I'm not sure what they do, though.
Yeah. Anyone else? That is a potentiometer or a variable resistor. So the way this works, and this is pretty old school, you wouldn't see this much anymore, but you've got contacts here in the middle. On this paddle is an electrical contact, and this is a coil of wire. And if you slid this paddle towards the bottom, you would probably have very low resistance. And as you slide it to the right, you increase the resistance because you're adding more coils of wire. Okay, and that's designed to have a certain resistance that it changes between. We'll use potentiometers in our class, but they'll be much smaller and there'll be a little dial. But this is basically a way of creating a variable resistance. And so motors respond to current. I'm going to try my pen again, even though history suggests it's not going to work. Oh, this is so weird. Okay, so I'm going to break out of this for a second. And slideshow. Okay, you can still see my slides, but they're in like edit mode, right?
Yes, sir. Yes.
Yes, sir.
Okay, great. That should work for what I'm going to do. Okay, so we're talking about this example here. Make that as big as I can. Okay, so we've got this variable resistor, and how does it work? There we go. Pin test. Okay, can you see that? Right, I'm writing on here. So the way a variable resistor might work is, say you've got a voltage source and you've got this resistor, and I put an arrow through it like this, indicating that it can change. So that means it's a variable resistor. Then we have a motor that can rotate. Okay, so, and then we go to ground. The way this variable resistor model would work is as we change the resistance, the current through the circuit will change. Okay, and so more current, motor spins faster, less current, motor spins slower. So what are the advantages of using this variable resistor design? Well, it's simple, and maybe it's easy to understand. That's the end of the pros. There's many cons. What do you think some of the cons would be? Disadvantages of doing this?
Maybe inefficient with the power source?
Yep, it's very inefficient. It's inefficient because any current that you're not putting through the motor, or voltage that's not going through the motor, is being burned up in the resistor. And what is it turning into?
Heat.
Heat. Okay, so we're just turning voltage into heat. We're doing the opposite of we're increasing entropy, and we're just we're making energy lower quality. Okay, so it's inefficient. It's also big. It takes up a lot of space. It's heavy. It has moving parts. What's the problem with moving parts?
They break.
They break. How do they break? They wear. Okay, they wear out over time, then they break. Okay, this is also going to be slow relative to what? What would we rather do? What would be better than this?
If we could vary the voltage directly via the source.
Okay. What's a technique for doing that?
PWM.
PWM. We can use pulse width modulation. So we could, if we had a power source that we could turn the voltage up and down, we could control the motor that way. But if you've got a power supply like the one we use in the lab and you turn that knob, how do you think it's actually changing that power, that voltage? Is it somehow so the voltage comes out of the wall, it's 110 volts. It converts it to DC to give us a DC power supply. Does that 110 volts from the wall change when you turn the dial on your voltage source?
No.
No.
No. All you're doing is you're using a potentiometer, some kind of variable resistor like this guy. You're wasting energy again. Okay, so our Arduino, does it have a variable voltage supply? No, it doesn't. It does not. It can only output 0 volts or 5 volts. Those are our choices. Okay, but we can use pulse width modulation to simulate intermediate voltages. And pulse width modulation is very efficient because we're never burning up voltage in a resistor. So no resistive losses. We're always using all of the voltage or we're turning it all off and we're not using anything. It's very robust, meaning it will survive. It works well in a long period of time. It can use entirely digital circuitry. That's a huge advantage because everything these days is digital. Now, your book talked about the advantages of using a higher PWM frequency. So, well, let's touch on that later. Let's talk a little bit about what pulse width modulation is. Okay, can we see this all right? I'll go back to slideshow mode. All right, so pulse width modulation means we are going to modulate or change the width of the pulses, the digital pulses that we output. Okay, so it's maybe easiest to look at this third row here. This has what's called a duty cycle of 50%. So that means 50% of the time the pulse is all the way on, and 50% of the time the pulse is all the way off. And we're going to change the amount of voltage that the motor sees by varying the width of those pulses. So for a 10% duty cycle on the top line or a 90% on the bottom line. So how do you actually calculate it? It's just some fun geometry here. Some key components of this. We've got the period is Y. I'm going to exit out of this so I can write on here. So Y is the period. We have X is the pulse width, and that might be in like milliseconds. The duty cycle is a percentage, and that is going to be calculated as X over Y. Okay, that might come up on a GR or a quiz or something like that. Okay, a standard hobby servo like the one I have here is generally expecting a 20 millisecond period. So that means it's expecting a pulse every 20 milliseconds. And then the size of that pulse is going to tell the servo which position to go to. So if it sees a pulse, so if X is 1.3 milliseconds, it's going to position itself at 0. in the middle, or which would be like, might be all the way counterclockwise. And then if it gets a pulse that's 1.5 milliseconds, it'll go to 90 degrees, which would be the center of its rotation. A standard hobby servo is going to rotate 0 to 180 degrees. That's the way a servo is going to respond to a pulse width modulated signal. If you just took a standard DC motor, it's going to just spin, and as you increase the pulse width, it's going to spin faster and faster because over time, it's getting more energy from your power source. So here's an example of what I was just showing. So if you looked at that chart, it said 1.5 milliseconds, which is the same as 1500 microseconds. Okay, so remember that for the next chart. This is just showing the behavior of a servo in response to the different pulse widths. This is for what's known as a continuous rotation servo. That's what we're going to use to power the wheels of our robots. Okay, so a typical hobby servo just positions from 0 to 180 degrees. It doesn't do a complete rotation. You can get a modified version of that called a continuous rotation servo, which will rotate indefinitely. And those can be used to drive wheels. If you give it that 1500 microsecond pulse width, it will stop. It won't go anywhere. If you give it a higher pulse width than that, it will rotate counterclockwise. Otherwise, it will rotate clockwise if it's a lower than 1500 microseconds. Okay. All right, so let's do a little demo. I'm going to stop sharing my screen. Can you see me?
Yes, sir.
Okay, great. So here is, I'm running a piece of code. You're going to create code like this in your next lab. Okay, lab 2 next week. So you've got a servo. Here's my Arduino. It's downloading the code right now. It's compiling. You'll see the light flash as it, okay, and then the servo just moved. I've written, I've made an enhancement to this. You'll do several versions of this code in the lab. You will just, the most basic, you'll just tell it, your servo, to go to a certain position. You'll run the code and it will go to that position. You'll also set it up to respond to a potentiometer. So you can turn the potentiometer and the servo will turn in response to that. That'll be pretty fun. You'll be pretty excited when you get that working. Here we go. I've written some code so that I can type in a position and it should go to that position. Okay, so did anyone see? So watch carefully, you'll see it move. I'm going to position it to 0. Okay, here's 180. Okay, and so what I'm showing you here is a bit of extra credit you can do for your lab. Okay, so that's controlling a servo with pulse width modulation. Another thing we can do with pulse width modulation, right, and I'll say a servo has to be controlled with pulse width modulation. It's the only way it will respond. If you just put voltage up to this thing, nothing will happen. It's listening for that pulse. That's every 20 milliseconds. So that's 50 hertz, and it's expecting a certain size pulse. What I'm going to show you now is if you just wanted to use pulse width modulation in general to create a variable voltage. So here's a good background. I'm showing you an LED, a light emitting diode that's getting darker and brighter. And what's happening, let me do that. Seems like you can't even see it get dark. It's going dark right now.
So you have to hold it in front of your face a little bit. Oh,
never mind. That work better?
I was a little zoomed in. Sorry.
Okay. I was holding it in front of my TV back there, thinking that that's a nice dark background. It might show better. What's happening is I've written code that goes through a loop and it changes the pulse width modulation value so that it's getting lower and higher voltage overall. You'd have to do this with an LED. An LED is a special type of device, and we'll talk about them later when we get to transistors. But an LED is basically always on or always off. It doesn't have an intermediate setting. It's not an analog device. It's a digital device. But we can make it appear that we can dim the LED by sending it a pulse width modulated signal where we're not giving it 5 volts 100% of the time. We're varying how much we're giving it. And so I'm using the Arduino code to go through a loop to fade it up and down. I'm going to share that code with you right now so you can see how that works. Okay, so you should be able to see a little Arduino sketch, and this is actually built into your code. You guys, if you've installed the IDE, you have this code too. You go File, Examples, Analog, and then Fading. This guy right here. So this is the sketch. There's some setup. It's declaring that pin 13 is going to be the pin that we're going to use. So that's where it's going to send these voltages to. Then it's got a loop here, and here it's a for loop. So it says for. So as long as the conditions within these brackets are true, it will do the following operations. So it's setting a fade value. The fade value is going to vary from 0 to 255. All of the pins on the Arduino, the digital pins up here in this row, they say PWM, meaning they can be used as pulse width modulation pins. You can send an output. You can output a voltage on that pin that's pulse width modulated. And you use the command analog write to do that. And then you have to specify in the function the pin number and the fading value. Okay, so if I said analog write 13, 0, I'd be sending 0 voltage to pin 13. If I said analog write 0 255, I'd be sending 5 volts to that pin. It'd be 100% duty cycle. So it ranges from 0 to 255, and this loop just steps through one at a time and increases that fade value by 5 every time it goes through the loop. So it adds 5 to the fade value, then it goes back through the loop and does it again. So it fades up, and then in this part of the code, it fades down from 255 down to 0 by subtracting 5 every time it goes through the loop. Okay? And then when it gets down to this curly bracket, it goes back up here and does it again. What if we wanted to make it fade faster or faster? Anyone?
Would you want a larger fade value?
You could do that. Yep, you could do that. What I've done here is I've changed the delay. So it has this delay in here. So it holds to each value for a certain amount of time before it goes to the next value, before it goes to the loop again. If it was at 60, I just changed it to 20. So if I run this, it should, I'm going to stop sharing so you can see me. It should fade up and fade down a lot faster. Here you go. See that pulsing faster now? Okay, cool. That's it. We're out of time. I ran